let's start then. Okay, so I'll be discussing roughly the theoretical in details our experiment, and then we'll talk about the results and their implications. This talk is intended to be accessible to the undergraduate students. So that's why it's going to be very long. So, I mean, the beginning part, at least 1/3 of it, is for the students, undergrads and postgraduates, and for non-particle physicists. So many of you who are experts, who are high-energy physicists, might find it very boring. But I mean, in that case, you can skip at least that part or not pay attention as you like. But this part will be very important to the students in order for them to understand the rest of the talk. Given the nature of this organization CASI lab, I designed this talk especially for the students. Okay. Here's the outline. So first I will give one slide on how science works, because it's about new physics, right? So we need to understand what do we mean by that. And then what are muons and what is G in g-2 and all. Then some issues with theoretical calculations, and then a history of the experiments, and then the results. See, on the right you see a nice picture where the muon is standing alone, and on right side, muon is covered by all sorts of particles that we know and maybe some that we don't know yet about. Okay, so if the muon is alone, then G is 2. When it's not alone, G is not equal to 2, and we'll discuss what that means later. All right, so how science works. Someone notices that apple falls, and they ask, like, why do they fall? Ghosts pulling them. Okay, that's a bad model, but yeah. Then someone else gives a model that answers why the apples fall, and along with that they give some predictions, like okay, how long will the apple take if you throw it from a building versus throw it from somewhere else, like that. So what is the time of flight of the apple? So this model that someone gave, they predict what that time of flight should be. Now some other guys come and they conduct an experiment, and they measure this time of flight very, very precisely, given the technology available to them and the time and money. And then what result they get in their experiment, the measurement, they compare this with the theoretical result. And if there is a difference large enough, greater than 5 sigma, what that means I will explain. But let's say greater than some value, that the experimental measurement is not matching with what the theory said it would be. In that case, we say, okay, the theory is incomplete. We need a new model that can explain this discrepancy. So 5 sigma roughly means that it could be a chance, an accident, that the theoretical result is not matching with the experimental result, but the chance of this being an accident is 1 in a million. It's really, really almost impossible that this is an accident. So we say, yeah, this is a discovery that we need a new model. Today, our apple will be the magnetic moment of this particle muon. And the model in question will be the standard model of physics, which is the established physics that contains everything we know for sure about physics, about nature, because everything else derives from physics. Okay. The motivation is that why g-2 and all? I mean, we could be doing anything else. And people are doing many experiments on many other things. But why this is very exciting for us, because 20 years ago, another experiment at Brookhaven National Laboratory measured this quantity that I will discuss what this quantity is, basically magnetic moment of a particle, and they found a difference between their measurement and the theory of 3.7 sigma. I said, I mean, it has to be 5 sigma to be absolutely sure that it's a discovery. But 3.7, almost 4 sigma, it's quite exciting. Okay, maybe if we increase our precision, if we measure more, measure in a better way with more precision. Precision means more precisely. Like, for example, if you measure the length of a football field with a ruler versus if you measure it with a hair, so the second one will surely have less error and more precise. So that's what I mean. So if you measure it better and better, maybe the difference between the theoretical result and the experimental will increase from 3.7 to 5 sigma and even more. So that was our expectation, and that's how we started to think about the new experiment at Fermilab that has many advantages, and of course 20 years of technological development that will help us. Okay, so what are muons? Muons are just like electrons, let's say. They're same in every way. They have the same spin, electric charge. They're called leptons. They belong to the same family. The difference is basically in their mass. So the muon is almost 200 times massive than the electrons. Let me just check if... Okay. 200 times massive than the electron. Other than that, everything is quite same. So they're like cousins. Now, what is G in this G minus 2? This is a very basic stuff, even for, I think for the undergraduate students. So consider this body, a rigid body with a charge distribution, uniform charge distribution. The total charge is Q, and it has a mass that also is uniformly distributed. And it's spinning with an angular frequency of omega. Now, the magnetic moment of this particular body in classical physics is given by this quantity, R cross J d tau. J is current density. R is, it's distance from the origin to the position vector to a particular volume element d tau. M is the magnetic moment. If you expand the current density in terms of this, the angular frequency and the charge density, then it takes this form omega cross R rho. If we substitute that, now we can also substitute this charge density rho in terms of mass density, because they're both uniformly distributed. So the charge density is Q over the volume, and then you do Q over mass, and then mass over volume. Mass over volume becomes the mass density. And if we substitute that, then this particular term inside the integral is nothing but the angular momentum of this body, the spinning top, let's say, from inception. Now, this is a classical relation, of course, the relation between magnetic moment and the angular momentum. And there is a factor of Q over 2m. Now, this quantity has to be corrected a little bit when we talk about quantum mechanics due to many various factors. Experimentally, it has been seen that there has to be a factor inserted in general, G. Oh, the G could be 1, of course. Okay, let me check the chat. Okay, so the question is, okay, the question, let me answer this. The question is, the value of sigma may differ in different experiments. So which minimum value of sigma required so that we can think about new model in physics? What does sigma really mean? So this is a good question. So when we do an experiment, you have a mean value and an error. Of course, no experiment can be perfectly precise. There is an error in everything, like statistical error or the limitation of your instrument. So that error, or let's say standard deviation, is what I call the sigma. Similarly, in theoretical calculation also there will be an error because of some approximation that you did. So that I call the sigma because it has a distribution of like a Gaussian. So the sigma is standard deviation of that Gaussian with respect to the mean. Now, consider any experiment, in this case our experiment, and it has a error of this size. At the same time, the theoretical value has a standard error of that size. Now you take the difference between the mean of the theory and the mean of the experiment, and then you also combine the errors. You have to know the error analysis in doing your lab studies, in undergrads. So you also have to take the combined error on this difference quantity, theoretical value minus experimental value. And so you get a combined error on that quantity. Now that we call the standard deviation on this difference value, so theory minus experiment. Now, if this difference in mean of the theory and the experiment is, let's say, 5 times the size of its error, then you are sure that the error is not large enough. So it is 5 times the error, this difference. And so that's what I mean by 5 sigma. But in this particular context, there can be more discussions. We can discuss it later. Okay. Okay, I will, this was crucial, so I just did that. Otherwise, I will answer the questions later. Okay, so we need a G factor to correct this classical the formula. Everything else works, really. This is a pretty good formula that works even for quantum mechanics. Now, imagine that the spin half leptons, the electrons and muons, are as spinning tops. I'm saying imagine, stressing, because they are not really spinning. You can't imagine them. You can't really think that they're spinning. Just imagine. They're not spinning. Spin is a quantum number really attached to that particle, just like charge or mass. It's not really physically spinning. Okay, if you imagine that an electron or a muon or all these particles are spinning with an angular momentum of h cross over, then of course you can put that value of L, if you can replace that value of L, angular momentum, with this particular value, in this case the h cross over 2. Now this has been found experimentally also, that in that case this particular factor G has to be 2, or let's say close to 2, at least experimentally. They found out to be almost 2. And Dirac actually could derive this from his theory exactly to be equal to 2. So consider this equation in the box, the big equation. It's basically Dirac's equation of relativistic quantum mechanics, an extension of Schrödinger's equation. So you can think of it as really a Schrödinger equation. So in a lower energy limit of Dirac equation, this equation takes this form. And you know that what is inside this, okay? Inside this is basically the Hamiltonian operator. So on this side we have kinetic energy term, and on this side we have potential energy term. And you know, I mean, all of you know basically in physics that the potential energy of a system of a magnet, let's say a bar magnet, if you put a bar magnet in a magnetic field B, then it starts precessing. and the potential energy of that system is given by minus m, the magnetic moment, dot b, the strength of the magnetic field. Experiment found that it's not, because if g equal to 2, it would imply that there should not be any difference between the energy levels of 2s half and 2p half of hydrogen atom. You know what those quantities are, right, from chemistry. So those orbitals will have zero difference. They would be degenerate if g was 2. This can be shown theoretically, but it has been found that those two levels differ slightly. Their emitted photons have a frequency difference of 1058 megahertz, really tiny. So that implied that g is greater than 2. And at that point, it was again the new physics, a big moment, news that, yeah, we need a new physics, we need a new model, new theory to explain this, because the Dirac equation was everything that we know at that point. So we needed something more at that point. That was a moment of truth. Okay. Soon, actually, it fueled the development of what we know as the quantum electrodynamics. There are many more people involved, but you know there's 3 people. Tomonaga, Schwinger, and Feynman. They got the Nobel Prize in 1965 for the QED development. So it fueled the QED. So I will discuss a little bit about QED, Feynman diagrams in general, but this is not a course on Feynman diagrams. This is a naive, very simple, just to introduce you to the notion of what they are. So the expert, I expect they forgive me for this. Okay, so naive Feynman diagrams. It's lagging a bit, the slide. Okay, these are not Feynman diagrams, but they're the diagrams of Feynman drawn by him. So I was talking more about these things. All right, in QED, quantum electrodynamics, there are basically 3 fundamental diagrams. Let's say pieces, the bricks of the building. So you have a photon, you have an electron, and you have a positron. It can be other particles also, but same type. It can be muon, anti-muon, and photon, but always, these 3 together. So one kind, like if it's a muon, then mu plus and mu minus and gamma. If it's electron, E plus, E minus, and gamma, and so on. Let's consider just electron to be simple. So these are the fundamental building blocks. You can build anything with them, but you have to follow some rules. Let me check if there is any question. Okay, nothing much. Okay, so if we can join them only in this particular combination. The orientation can be any, but there should be this one particle, one lepton, because electron, muons, they're called leptons, one lepton coming and going out this way, and at the point of their kink, there should be a photon connected. This is the most basic, let's say, joining them together. You can join multiple of them again, but you have to always remember that the vertex where they meet should be always like this. This is called a QED vertex. Now let's consider a few of them. They're oriented in different ways. For example, the first one would mean that an electron is coming, it's emitting a photon, and then it's moving on. Okay. The second one would be an electron, a positron absorbs a photon and moves on, and so on. The last one, for example, is a photon creating an electron-positron pair. Now we can join such diagrams together. You see that at each vertex it obeys the rule that the lepton and the photon here also. And like that, we can join diagrams and build things up, okay? We can join them even this way. The rule is not broken. And this actually means a photon converts into a virtual electron-positron pair, and then those virtual electron-positron pair come together, annihilate each other, and create the photon back. I say virtual because you don't detect them, you don't see them. Only the photon that is coming sees it. And they're in the vacuum, they're coming up, popping up and disappearing. They're existing for such a short amount of time, allowed by the uncertainty principle, but you are not able to detect them physically. That's why they're virtual. Okay, so these kind of diagrams are called loops. Okay, they create a loop in the middle. It's like the photon can, so here can be a muon coming, going out, leaving a photon, and then that photon here creates a loop and things like that, okay? In the vacuum. It's called, the photon is interacting with the vacuum. So vacuum is filled with such particle-antiparticle pairs. So the vacuum is not really a vacuum. Okay, we can join things like that. But the good news is that the more complex the diagram becomes, in the sense that the more and more vertices it has, the less and less important they are. So we don't have to really, in principle, we should calculate because all of this diagram actually correspond to a number. That's why I said calculate. So we have to, in principle, draw infinite number of such diagrams in all possible way, only leaving the end of the two ends fixed. Like one photon has to enter, that same photon has to leave. In the middle, you can do whatever you want, more complex things you can build. And in principle, you have to build all sorts of diagrams. But that would be impossible job, right? Fortunately, the more and more complex they become, the less and less important that they become. So basically, you have to calculate a few diagrams in practice, considering how accurate the result you want. And trust me, it gets really accurate after 2-3 orders in complexity. So this is very good. Okay, using such diagrams, people calculated the lowest order in g-2. Remember that I said the experiment found that g can't be 2, it has to be greater than 2. That means g-2 should not be 0. It should be a positive number. So the simplest calculation is this tree diagram without any loop involved. There is no loop, the most basic diagram. This gives g equal to 2, which means g-2 is 0. So this diagram has 0 contribution to g-2. The first contribution will come from such a diagram. Let's say an electron is coming, leaving a photon going on, and that photon is absorbed by the positron. And the positron and electron meet here. And that can be interpreted like this. But basically what it means physically is that a particle, electron or muon, is just interacting with an electromagnetic field, and it's also interacting with other photons in the vacuum. Other pairs of particles in the vacuum. In this part, so this is a kind of loop here, different than what I showed you earlier, but this is still a loop, and it's interacting with these particles in the vacuum. Okay. Schwinger actually calculated this number. There are, of course, more complicated diagrams, more loops, but let's consider the simple one, the first one, this one. And he calculated this value for the first time. And he found a number alpha over 2 pi. You know what alpha is? Alpha is the fine structure constant, which is roughly 1 over 137. And the value came out to be this, which means g equal to 2 plus this extra tiny 0.00232. So now you know what is g and what is g-2, right? Okay, let's proceed. So this result was so, fantastic that it got engraved on the grave of Schwinger, which is kind of sad but beautiful. Okay. And this, of course, explained why those two energy levels were different. Because you see, the shape of s orbital is very different from the shape of the p orbital. So they get kicked differently in vacuum, and that contributes to slightly different energy results. Okay. But, I mean, these loops that I talked about are very important. And they could be hiding things, because I said there can be any complicated diagrams possible you can imagine. And they should be like, that means that in vacuum, because when I said loop, I said that they're basically, the particles in the loops are virtual particles that are popping up in the vacuum and disappearing. So in principle, in vacuum, any particle and its antiparticle can pop up and they can disappear, which means all the particles that we know, but which also means that if there are unknown particles that we don't know about, we have never detected or never got any signs of them, they will also be popping up and disappearing, and which means our known particles, let's say muon, can interact with them. It doesn't matter whether we know about those particles or not. We have a theory to calculate those particles, use that information or not. But the muon is a physical particle, and when it passes through vacuum, it will be interacting with those unknown mysterious particles that we haven't discovered. That's why the loops are important. So the blob here represents whatever things that go inside in the vacuum, like known particles, unknown particles. So the blob includes all the particles that we know about. Let's call them the SM particles, the standard model particles, plus the unknowns. Of course, the unknowns are accessible only through precise enough experiment. Through theory, you cannot access them because theory is limited by what you know now. What is your model? How many particles you have in your theory? You can only calculate the contributions from them. You can not know about the unknowns as of now. So let's write down this extra thing, like g equal to 2 plus, let's say, extra, which is called the anomaly and the interesting part. So we define this extra part as g minus 2 over 2. Let me close the window because of our canine friends. Okay. So this anomaly, or the extra part that is interesting, is g minus 2 over 2. This we denote by A, and the suffix L here represents any lepton. It can be the anomaly of the muon, of the electron, of the tau. Okay, so the AL can be written down. Here AL means the whole contribution that can give rise to a value of the anomaly. Equal to a standard model part in green that we can calculate precisely, and an extra part maybe from new physics that we don't know about. Okay. So this new physics will be coming from the unknown particles or forces. Okay. But we have to calculate this part very precisely, and we have to then measure the whole thing in the experiment very precisely. Only then we can take a difference between this, and what we will be left with is this part in yellow, and that will be our new physics. Now, how do we access the new physics? I mean, suppose there is an unknown particle in the vacuum. It's coming, it's appearing with its antiparticle, and it's interacting with our lepton. What will be its, let's say, theoretical signature? What will be its contribution? How big it will be? And what will be its form? For that, let's consider, I think I'm going very slow, but only this part will be really slower Please stay with me. I expect you to give me some time for that. Okay, for the sake of students. Okay, so consider a particle, unknown particle of mass m loop running in some loop, okay, in a diagram, in some, I mean, in a calculation of this anomaly. Now, if that is so, it turns out that a contribution to this quantity AL from such a diagram where there is an unknown particle of mass m loop is running will be proportional to mass square of the particle that you were considering, like the, you know, the anomaly of the muon or the electron, the mass square of that particle divided by the mass square of that unknown particle. And so that's how it comes up in your theoretical calculation. So this actually explains, if nobody has asked, let me answer that, but why do we consider muon and why not electron, or even tau? So, I mean, look at this term. If you calculate this m electron mass square divided by m loop, of course this particle m is something heavier than electron, but that's not important. The important thing is that this whole quantity is mass square of electron divided by this unknown mass, and if you consider muon, that will be mass of muon square divided by this thing. If you compare these two numbers, you see that there is a difference of 43,000. So muon, if it's the anomaly of muon that we are calculating, it will be 43,000 more sensitive to detect an unknown particle, you know, compared to electrons. So obviously, we will go for muon. And besides, this quantity will be almost zero if you consider electron, and it will not be detectable in current experiments, even if it's, I mean, sensing an unknown particle. This quantity will be tiny, so we need something bigger on the numerator. That's why muon. But then the question will be, why not tau? Because tau is even 17 times heavier than mu. Well, tau really lives for really short time, 10 to the power minus 13 seconds. And we don't have any technology right now to measure anything with such a short-lived particle to extract its magnetic moment. And therefore, tau is basically useless right now for us. The best option is the muon. Okay. All right. So now I'm going to discuss the actual calculation using the standard model of physics, the physics that we currently know about, established physics. Standard model calculations of this quantity receives three kinds of contributions. And of course, you can guess they're coming from three kinds of forces. The electromagnetic force, the weak force, you know, beta decay, and the strong force. So there are these three contributions basically. Well, the fourth force is gravity, which has, let's say, zero contribution in this whole business right now, unless you're traveling inside a black hole. But, okay, so we are here. But the problem with the QCD part, the strong force part, which the theory of which is called QCD, the quantum chromodynamics, like quantum electrodynamics. The charges are called colors charges, and that's why the chromo factor is there. Okay, everything is fine with the QED and QC, electroweak thing though. Electroweak I said because it's weak plus electromagnetic. They are combined together to be electroweak. Okay, they're fine. You can calculate with extreme precisions the contribution coming from these kinds of diagrams. But for the last kind of diagram, inside this yellow blob, what is running is hadrons. Hadrons means particles that interact through strong force. They are like quarks, gluons, and their combinations, pions, kaons, etc. this part is very messy because the quantum chromodynamics is fundamentally very different compared to the other two. You can imagine the quarks to be connected by a spring, and you know, if you pull them apart, they start to pull back stronger and stronger, which actually means, in terms of the Feynman diagrams, very naively, that the more complex diagrams you take now, they become more and more important. So in principle, you consider infinite number of diagrams, you have to in principle, and the whole result blows up. So actually this thing altogether doesn't make any sense, because this is a perturbation theory. Perturbation series must converge, and this is a disaster. This method won't work in this kind of force. So people will have to resort to other methods that are not perturbation theory based. They're called non-perturbative methods. And they often involved the best method they came up with are actually two kinds. I'll discuss them one by one. But the fact that they're approximate methods, like they depend on data or the computer power, so they are limited by those things, and currently they have large errors. So basically this third kind of contribution that is coming from QCD gives the biggest error in the whole calculation. The other two are amazingly precise. Okay. So as I said, there are two particular kind of approach in to calculate this hadronic, the quantum chromodynamics contribution. The first method is called the dispersive approach, where I'm not going to discuss the whole theory here. It's on, it will be a whole new talk, and theoretical physicists will be able to explain this better. Basically, it means that you use a partly theoretical calculation, and you need some input from the experiment. You consider a diagram like this, and by the principle of dispersion relations, and which is actually coming from what is called the unitarity of the S matrix, that I'll not elaborate here, but basically that means the probability is conserved. You can, by a theorem that says that you can cut this diagram into half, and what you get here is this photon going to all sorts of things here. Now, it has, in the denominator, it has this S, which is the center of mass energy. And as it is in the denominator, which means smaller and smaller this number, the bigger will be the contribution from this, for this integral from the smaller energy part. So basically this electron, positron going into a photon, and they going into hadrons. So basically E plus E minus based experiments are used to calculate this theoretical value. And the error is coming from the experimental data. You know, what is the error in the experiment will be entering in the theoretical calculation. So it's not a purely theoretical calculation, really. The next method is actually purely theoretical. It is called a Lattice Qcd. So it is actually absolutely the QCD theory. No approximation yet, but there is approximation, but it's a different sort. But it's completely theoretical based. In the Lattice Qcd, what they do is they imagine the space-time to be discrete lattice with a spacing of A. And of course, you are going to then use this in computers to calculate things after discretization. Integrals become summations. And you can't have an infinite space, okay? 0 to infinity is impossible. So you have to approximate with a very large but finite space. You also need an extent of time which is limited and not infinite. And those are the limitations that are entering into the calculation that is coming. So this actually now depends on the computational power that we have. The more and more the computers develop into faster versions, they will get much better results. Right now the error is big. It's 2% on, okay, there are two kinds of diagrams that I will not discuss into detail, but this is the lowest kind of diagram that we can imagine coming from the quantum chromodynamics. There is another kind of diagram that is called HLBL, has even bigger error. 45% is just error. Okay, so that's the limitation. This slide I'm sharing with you the entire standard model results calculated by the theoretical community. And this community is called the G-2 Theory Initiative. This is their website. You can go there and get all the details about, I mean, even on their homepage, all the results, methods, calculation plots, and numbers and everything. This is a big collaboration of theoretical physicists with a drive to calculate the G-2 theoretically inside standard model as precise as possible, so that they can compare their value with the experiments. So this is the number that we get for this A mu, which is G-2/2. This tiny number is what they calculated. This quantity in the bracket means is the uncertainty on the last two digits. So you're sure, they're saying that these numbers are sure, but the last, these on these two digits, they have an uncertainty of plus minus 43. And this is the summary of the results coming from various contributions. So you can see that the quantum electrodynamics QED contribution gives almost 99.99% contribution to the G-2. And the rest is tiny. This electrowave gives 0.001%. The hadronic gives about 0.001% contribution to the G-2. Everything is almost coming from QED. All right, prior to 7th April this year, they compared the result with a previous experiment at Brookhaven. And they found that this difference is 3.7 sigma that I quoted earlier. And this was very exciting. But that was prior to 7th April, okay? And they were like huge amount of conferences discussing what could this mean. And of course this motivated us to do the experiment, but this also motivated the theoretician to go for starting to find even new physics theories that could explain this already, even though it is not 5 sigma yet, but they were excited. So this was a big motivation for everyone, actually. Okay, let's discuss the experiments now. Briefly, a history. It started in 1957 at Nevis cyclotron. The technology used was very different, and you can see the first value was g=2, and the error on this quantity was 100,000 ppm. Okay, let me explain what ppm is for non-particle physicists. Okay, many of you know it, but for students, maybe they are not, acquainted with this particular unit. Okay, it's like a percentage, really. So percentage could be rephrased as part per 100. The same way, if you replace 100 by 1 million, then that would be ppm. By 1 billion, that will be ppb. So it's like part per 100 is percent. A cent means 100, and this is part per million, part per billion. Well, the next experiment was in 1957 at the Liverpool cyclotron. And you see from 100,000 to 7,000 ppm. So the precision jumped. You see, this was the error bar. Let's say the size of the error bar was this, and the next experiment, almost like at the same year, and it shrank to this value, 7,000. The next experiment was CERN, and you see the error bar has shrunk to 0.3 from 7,000 ppm to 0.3 ppm. Sorry, that number should be corrected. It's not 0.3 ppm. It's a wrong unit here coming from the PowerPoint slide. It's here, 5,000 ppm. Sorry, extremely sorry for that, because we don't have 0.3 ppm yet in any experiment, but we will have after next year. Okay, the first CERN experiment achieved the 5,000 ppm result. There was another CERN experiment with entirely new technologies. Now, this principle, more or less, not entirely, but it's a storage ring based. What is a storage ring? I'll explain later. But this base experiment, and that achieved a jump of precision again. It became 266 part per million. You see, from 5,000 to 260 ppm. We're getting more and more precise in a few years. And you are seeing that the G value is changing now. Okay, this is not G mu equal to though. This is it's a wrong number here. I'm sorry for that. It should be 2 point something, of course, because G is equal to 2 point something. Yeah, so now the next third experiment is actually in CERN, they started to use the technology that we use still now, but much improved, but the principle is the same. And they achieved a 7.3 part per million precision in the experiment. Okay. Okay. If there is any problem like in streaming or sharing or anything, please let me know. Otherwise, I might be going on maybe without internet and I don't know about it. All right, so the CERN third experiment. Now comes the Brookhaven experiment that I have been referring to so much, the most exciting one. Okay. Brookhaven achieved a precision of 0.54 part per million. So it has gone to now sub-part per million level. This technology, this principle of experiment we will be using too. And of course, there was a difference found between the theory and experiment of almost 4 sigma, and this inspired us, and there was a big move. So the ring, the storage ring where the muons were stored for this experiment is a big magnet, is a 14-meter diameter big iron magnet, super conducting magnet. And it was, it was pointless to start building another one. It's a huge waste of money, and I think you will not get a fund for that if you already have an amazing magnet that is already there, have been used in Brookhaven. So, and it was performing amazingly well. So we decided, okay, let's use their magnet. But of course you have to travel like 5,000 kilometers, and you can't just go from here to here by road because, mountains and lots of stuff. And you cannot, create stress on the magnet. You cannot put shear force on it. Otherwise, it will just damage it, because we need amazingly stable magnetic field produced by this. So it was a big move, because then they decided a smooth journey will be through the sea and then through the Illinois River up to this point, and just a tiny roadway, So that's what has been done. So it happened during the June to July 2013, through sea, through river, and through the roads. When it arrived, it was a big show. It was a big celebration at Fermilab. People gathered and all. Okay. check out the chat again. Okay. The whole campus that is involved in the Muon G-2 experiment. Recycler ring and all the Muon G-2 target station. I will say, well, I will explain what is a target, where actually, let's say, okay, where the protons are shot to a target, where they decay into, where they create pions and muons and all these things that I'll discuss later. And here, actually, you see this name MC1. This is this building that contains the whole storage ring, 14-meter diameter, and the control room, and every one of us. This is where the experiment happens. MC1 here, the building is the whole Fermi lab. It's and almost 200 collaborators. This in red is what the Italian collaboration is. INFN Naples is where I was from, and other cities. INFN is Istituto Nazionale di Fisica Nucleare, is the National Institute of Nuclear Physics, and they're the so basically this is us. There are a lot more people, actually. They were not here. We were attending this very important collaboration meeting, so we came here together at Fermi Lab in the Wilson Hall. This building, if you can still see, is an amazingly beautiful design. So this is where we secretly met for some secret discussions, you know, among all the Italian members. All right. This is a bigger picture of the whole Muon campus. This is MC1 building. All right. The working principle of the experiment. Very broadly, you shoot some protons and they produce a lot of shower of particles, but you're interested in the pions, pi plus actually, to be precise, and with a specific energy that I'll explain why we need that specific energy. And those pions, from those those pions decay into all sorts of things, but you need only the mu plus, the anti-muons from them. You separate them, you filter them in various ways. Maybe you know about it. I mean, you throw some charged particle in a magnetic field and they will bend, and they will bend accordingly. Like if it's a massive particle, they will bend less. If it's a lighter particle, it will bend more. So that way you know, stop the ones that are bending more and are bending less, and you can select only the ones that you want. Okay. So we take the mu plus. We say we need the polarized mu plus. And I'll explain what polarization means in this regard. You probably know about polarization of light, but what polarization that I'm talking about here, I'll explain. Okay. Purely polarized positive muons are extracted from that, and they're injected into the ring that I was showing you. That is everywhere in the newspaper, a big blue ring. We inject them inside, and they're circulating in a very stable vertical, stable vertical magnetic field. They circle around, they keep circling and dying, and eventually they all die out. They die out into positrons, and those positrons are what we actually detect in our detectors. And they convey a very important information that is crucial, so I'll explain it here. So the polarization in this regard means a particular orientation of their spin with respect to their momentum. So any of those, I mean, the spin could be either directed along the momentum or in the opposite, not in some random direction, okay? So in random direction is not polarized. Polarized in our case means the spin is either along the momentum or is in the opposite direction of the momentum. And we will see that comes actually naturally. We don't have to do anything to get polarized muons. They are born that way. And this is because of the nature of the weak interaction. So, of course, I'm not going to introduce the whole weak interaction here, but the only part that is relevant. The parity violation part. So, what it basically, the information here we need is something called the right-handed and the left-handed particles. Handedness is exactly what I explained. So if the particle has its spin along the direction of its momentum, then it's called a right-handed particle. If it's in the opposite direction, then it's called the left-handed particles. Now, in the standard model, the theory of the part that has weak interaction says that particles that are left-handed and antiparticles that are right-handed, only those take part in weak interaction, not the other way around. Left-handed antiparticles cannot interact, okay? They will just go past. They will not interact weakly, though. They can interact through electromagnetically. The same way you can left-handed antiparticles cannot interact through weak interaction. And this was theorized by these two guys, Li and Yang, and was proven experimentally in an amazing experiment by Chen-Shang Wu. I don't know if I pronounced it correctly, but yeah, I tried. Okay, so brilliant physicist, all of them. All right, this was an amazing discovery. And thanks to that particular property that we have by default polarized particles. Okay, so I said, so now consider that a particle is massless, okay? So, I mean, no, let's first start with a massive particle. Let's say a particle has some mass. Now, if a particle has a mass, and I said, let's say this particle was produced in a weak decay, in a weak interaction. So by the theory, the particle has to be left-handed, as it was produced through a weak interaction, okay? Which means it is left-handed. Produced, I mean, it was born left-handed, which means its direction of its spin is opposite to its momentum. But, I mean, you can run faster, right? You can run along its momentum. So the particle is running like this. You run behind, and you run really, really fast. And as this particle is massive particle, you can outrun it. I mean, you can, you can imagine outrunning it. And at some point, when you outrun this, its momentum will be in the opposite direction. It would appear that the particle is moving backward. At that point, actually, its spin and momentum is pointing in the same direction because the spin stays the same. The spin this way, momentum this way. They're going like that. You outrun it, and you see the momentum also this way. So if you have seen my video, you have seen me demonstrating this. Anyway, so a massive left-handed particle will become a right-handed particle. No problem. If you can outrun this, you can go to a frame where it's going in the opposite direction. But if the particle produced is massless, well, then the particle is produced left-handed, and in no frame you can go, or you cannot run faster than the particle.
Hello. Sorry for disturbing, but sorry for disturbing, sir. But this is only a concept, right? This means this is actually left-handed doesn't change to left-handed. It is actually left-handed, but as the speed is
just a moment. Can you write it down in the chat? I'll try. If it's a question, I'll try to answer. If it's a discussion, we can do it in the end because I took a lot of time. I think I should speed up. So sorry for that, but I will definitely try to answer your question, or I'll take part in the discussion if you stay till the end. Can you please type it in the chat? Okay. As we are testing the theory here. So I'm going to the experiment. And this is the standard model theory that if the particle is now massless and it was produced in a weak interaction, then the particle by definition is left-handed. and it's massless, so you cannot outrun it, so you cannot flip its momentum. So the left-handed particle remains left-handed for its life, and so right-handed particles remains right-handed always. And that's why, I mean, the neutrinos are produced, of course, neutrinos and antineutrinos produced in weak interaction. They don't have, charge, so they don't interact electromagnetically. They don't have a color charge, so they don't interact through strong force. They only interact through weak interaction. And that means they're produced always through a weak interaction. So if a neutrino is produced, it's produced left-handed. So because they're massless, let's say in standard model, but in practice their mass is tiny, tiny, very tiny. Okay. But let's consider massless. So neutrinos are always left-handed, and antineutrinos are always right-handed. Okay. All right. We will use this fact. Okay. But this also means that even if the particle is massive, let's say electron, but electron is very light, extremely light. So which means it will be hard to outrun them. So at least very high speed electrons that are produced in a weak interaction will be left-handed, and the positrons will be right-handed. Most of them, actually, most of them, let's say 99% of them, but they have a tiny mass. Some of them will be of the other kinds. Okay. All right. So here we need polarized muons, right? What we have is pions. Now pi plus, actually, I don't know, my mouse is not moving. Okay, now it's moving. So from the protons we get some pi plus, and those pi plus are decaying into muons. So let's go to the rest frame of this pi plus. Pi plus has a spin 0. Now in the rest frame, it's decaying into two particles. So in one direction, the muon neutrino will come out. The other direction, the muon, the anti-muon, will come out back to back, because to conserve the momentum, of course, and to conserve the spin. Of course, they will have to be directed in the opposite direction. Now look at this. This is a, let me check what this. I actually explained why muon and not electron or tau particle. What do you mean, like why the pion is decaying into muon and not electron or tau? Or I mean, what do you mean by the question that why muon, not electron or tau? Do you mean the g-2 of muon, or do you mean the pion decaying into muon and not electron? If you could, sir, if you could please clarify that. Okay, let me answer. Okay, as I have answered the previous one, that is why g-2 of muon. So I think he's asking about why I mean the muon is going to pion is going to muon and not electron or tau. Okay, the pion cannot go to tau. Tau is too heavy. It can go to electron also, but we are not interested in that. We need the muons, so we will select out the muons. We will filter out the muons only from the pion decay, because we need to calculate the g-2 of muon, so we need to filter them out. All right, so polarized muons. How do we get polarized muons? Yeah, this way. So when the pion decays into a mu neutrino and an anti-muon, the neutrino, by definition and by its property of massless in standard model, it will be left-handed, and it's going to stay left-handed, which means its spin will be in the opposite direction of its momentum, and momentum is in this direction, the spin is in this direction. So which means to conserve the angular momentum, because the spin is 0 of the initial particle pi plus, the mu plus, sorry, it's not a plus here, it should be mu plus. The spin of the muon will have to be directed opposite also to conserve the angular momentum. So this becomes also left-handed. So what we have got is all the left-handed muons actually. So you see, like by default 100% polarized muons. We don't have spins directed in every direction. We have only muons with spin directed exactly in the opposite direction of its momentum. All right. Now let's come to the muon part. So we collect these mu plus, these polarized mu's, the left-handed mu's, and we introduce them to our storage ring in the magnetic field. Now let's again go to the rest frame of this mu plus. Imagine its decay. It basically decays almost 100% into a positron and an electron neutrino and a muon antineutrino. Now, of course, it's a three-body decay, so all of them can go in any direction possible, even in the rest frame. The E plus could go this way, the nu mu this way, nu E this way. As long as they all together conserve the momentum, they're okay. But if we are going to consider let's say, the highest energy positron case, then this is the only scenario, because only then, to conserve the total momentum, these two will have to go in this direction and the positron will have to come out in this direction. This will be the highest energetic positron scenario, and that's the only one that we are interested in. Okay, so we got this scenario. Now look at this. So we have a antineutrino here, muon antineutrino. So by birth, by definition, is right-handed, as we explained in weak interaction, and an electron neutrino, which is a particle, so it's a left-handed. So it's spinning this way, the other one is spinning the other way, and these arrows are wrong. Sorry for that. Actually, this one will be spinning this way, this arrow will be spinning the other direction. This is right-handed, this is left-handed. So one spinning in this direction, the other spin in this direction. So they cancel out. So they cancel out their angular momentum. Okay? But the initial angular momentum was the spin of mu plus, which is half. And that is left to be cancelled out, right? And to conserve the angular momentum, these positron will have to have the exact same angular momentum, or the spin of the muon. So basically, the spin of this positron will be equal to the spin of the muon, its parent, to conserve the angular momentum. But what is this positron? It's an antiparticle, and by definition is produced as a right-handed particle. And we are considering the highest energy positron. Now, if we go back to our lab frame, then it's moving in this direction, all of them. And okay, so the momentum in this direction and the spin in the same direction, and it remains right-handed, of course. And it's the, of course, if we consider the highest energy positrons, then they are right-handed, even in the lab frame. But the parent muon, we saw that it was produced left-handed. It was left-handed, even in the lab frame. So we have got an initial left-handed muon and a product right-handed positron. And the given fact is that the spin of them have to be equal. So muon spin equal electron spin, which means we have got the left-handed muon, so the spin is opposite to the momentum, so S dot P becomes a negative quantity because they're directed opposite, and S dot P for the electron is positive. Now the S is same for both because of spin conservation, which means the momentum is opposite, and which means the momentum of electron will have to be parallel to the spin of the muon. So what we got in the end is that the highest energy positron that we will get will be ejected in the direction of the spin of the muon that it decayed from. So we are getting the information of the spin of the muon from the direction of the positron that is it was emitted. Not all positrons, but the highest energy positrons. Remember that. Okay. All right. So now coming to the final form of the principle. So now that the muons are inside the ring, this is the ring, they will have two kinds of, frequencies. The one, of course, they will be revolving in this ring, and they will have a cyclotron frequency, which is given by this expression. B is the magnetic field in which they're revolving, and mass of them, and gamma is the relativistic factor. Okay, 1 over square root of 1 minus v squared over c squared. That's gamma. And another one will be the spin precession frequency. Okay, Lermer plus what is this called? I'm forgetting that. So this is the spin precession frequency. And you see that here enters a factor g minus 2 by 2. It's called A mu, which is beautiful. Now you'll see where we're going. Now this will be the scenario happening. The muon, of course, enters with its spin directed along its momentum, but as soon as it enters a magnetic field, its spin starts to precess around its magnetic field. But it's also moving in a circle, so basically, like precessing and moving around in the whole ring like that. Okay, let's take the difference between these two frequencies. Okay, the difference turns out to be a beautiful form. The difference frequency we call the omega A. That is omega C minus omega S minus omega C. And it comes out to be in an amazing form. These are the magnetic field and constant, the electron charge, mass of muon, times the g minus 2 over 2. So basically what we need is just this quantity. So A mu equal to, you put this thing on the other side, you measure this frequency difference somehow, I'll explain how, and you got your anomaly, g minus 2 over 2. Okay? This is a very lucky formula that came up, really, like so simple. But it's not that simple. Well, when you introduce the muon into the ring, there is a little bit of imperfection, right? It doesn't go exactly into the orbit it should be. Slightly, you shoot it in a slight angle, or you kick it in a slight angle, and it is not exactly vertically focused. So to focus that vertically, otherwise, it will be just moving in upward direction and hitting the wall on the top and getting lost, and we have we don't have much data. What we want them to be in the stable orbit, and want them to be revolving in the ring for several times. So that's why we apply electric fields using electrostatic quadruples. Okay, so what is precession frequency? Okay, precession frequency is this, actually. The simple animation describes it here. Let me go back to the... Yeah, you see that animation there? You put a spin in a magnetic field, the magnetic field in the vertical direction, let's say. This is a gyromagnet, though. So if you know this gyroscope, so if you spin it and you put it on this or a top, spinning top, you will see that it's not just spinning, it's also wobbling. And so this wobbling thing, frequency of that, like the frequency of this wobble motion, how much time it takes to complete one wobble, is the frequency, inversion of that will give you the frequency of the particular, that motion is called precession. You take a top, it's spinning this way, and then it's also doing this. That motion is precession. So the time it takes, it's the time period, and the opposite of that is the frequency. I think that answers the question. Let's move on to the next part. So we need electrostatic quadrupoles to apply some electric field to keep the muons fixed vertically in the orbit. But this then introduces an extra term in this frequency. This frequency is the difference frequency, omega c minus omega a, the cyclotron frequency minus precession frequency. This here is not a, it should be s, the spin precession. A is the difference. So omega a is this quantity. We have got a nasty factor that complicates our life. Fortunately, we can get rid of this whole thing if we choose the energy of our muons very cleverly. So if we choose the energy to be around 3.1 GeV, it turns out that this term becomes close to this term, and they cancel out to give a value 0. Of course not absolutely 0, because this is an experimental. You have some slight spread over the energy, right? You can't have all 3.1 GeV. They will have slight deviation around that. So that's why the cancellation will not be perfect, but the mean value of that will be 0, and they will have a slight spread. Then we can apply some corrections later. But as far as the formula goes, the mean value goes, we get rid of that term. Then we are back to our simple formula again. That's why this momentum is called the magic momentum, and that's why we chose a particular energy of those protons so that we end up with this particular value of our muons. All right, now what is the implication of this formula? Look at this, the frequency difference of the cyclotron in the spin is proportional to g minus 2, right? So if g was exactly equal to 2, that would mean the spin difference is exactly 0, which means, not the spin difference, the frequency difference would be exactly 0. What would that mean? That would mean that if we start in this position, we complete one rotation and come back to the same position, both would have completed one revolution. Like the spin the cyclotron motion will complete one, of course, and the wobble will also complete, like slowly going around, and will come back to the same phase again. And in that case, we would get a difference in frequency to be 0. But if the g is not exactly 2, if it's slightly 2, then this quantity will be non-zero. And that would mean they will have a slight difference in their frequency. So when they complete one revolution, they will not be perfectly matching in phase. And that will mean that if you are sitting here, okay, if you are standing here and looking at the thing, so if a muon is here, its spin is directed towards you in a particular angle, next time it comes back, it will not be exactly directing towards you, but slightly, slightly in a different direction. Another revolution, it will be in slightly another direction, okay? Roughly it will take 12 such revolution to come back to direct to you. Which will mean that we remember this fact that, actually I put it here again, that the ejected positrons, the highest energy positrons, will be ejected exactly in the direction of the spin of the muon. So if you're standing here, let me see if there are any questions. No. So if you're standing here, by standing, I mean your detector is here, but let's imagine that the spin of the muon, or the muon, is like a torch, and switching on the torch means, the direction of the torch means the spin direction, okay? The muon spin, so the torch direction. If you click it, if you switch it on, the emitting light, imagine that as a positron emitting. And if we consider only the highest energy positrons, they will be emitted exactly along the direction of the spin of the muon. We proved that. And not in other directions, because we are considering only those electrons. Then, after one rotation, as the spin is slightly in other direction, you will not see that positron coming towards your direction. So you will see different counts of positrons coming towards in your direction after a revolution. Okay? So in the animation on the right side, it looks like you put a threshold on energy. That means you are considering only those electrons that are energetic enough so that their direction directed always in the spin direction. And this means the spin is precessing in the magnetic field, so moving like that in a circle. So some point you are standing here, you see, boom, you see the positron, then you don't see. So you see the number of positron detected starts oscillating because of the fact, this oscillation would be 0. You wouldn't see any oscillation if g was 2, but now you will see if g is not equal to 2. What will you see is something like this, a sinusoidal wave in the number of positrons that you detect. Is one calorimeter will see at some point the spin direction in this direction, so it's ejecting a positron in this direction. After one revolution, because the precession and the cyclotron frequency is not matching, the next time the spin will be slightly directing in the opposite direction, and you don't see that positron, so you see a down there. So you got an oscillation. So in the end, you got a plot like that. So why this plot? Because the exponential decay is understandable, right? It's the nature of any decay. You start with some particles that decay, they follow exponential. Right? The number right now is proportional to number you start with, and that's a logarithmic formula. You know from nuclear decay and nuclear physics and everything. So that is not, the exponential thing, the number of muons you start with will be slightly less next time because some died out, some more died out in the next revolution, and so on. After some time, they all will die out. But on top of that, you now have an oscillation due to the fact that the emitted positrons are sometimes directed towards you and sometimes not. And so on top of these exponential, you got a oscillation. Okay, I see number of people almost halved. All right, that's okay. People interest. Some people are probably busy, and some people got bored maybe, but that's fine. That's fine. Okay. So g not equal to 2 means an oscillating exponential. But don't get bored. We are just. This is important. This part, and then we will be just discussing the results. It's not much left really. So just to encourage you. Okay. So in the end, if you wrap this whole thing up, because this takes a lot of space. So you break it into multiple in sections of 100 nanoseconds, and you put it in one plot. So 100 nanoseconds, you cut it here, put it back here, then cut it back, put it here, and you see the number of positrons going down overall by a factor of 10 in every 100 nanoseconds. That because some muons have decayed out. So in every turn, some muons are dying, and so you're reducing. So you finish this whole thing after some, wrapping up. All right. So what we do is we need to find out this particular oscillating frequency. We know this frequency, we know omega A. And then we know, of course, a mu, just divide by this factor. Of course, we have to know this factor. And magnetic field is what we are creating, so we know, of course, this. And the E we know, charge of electron and the mass of muon. So this particular thing we have to fit, of course, it should have an exponential factor in front because of the exponential nature of decaying particles, and then an oscillation on top of that. So I think this is pretty intuitive that any one of you will come up with this formula, right? It's a 5-parameter formula. This tau is the lifetime of the muon, so that's why this exponential factor of the muon. Then you have a coefficient A, which means this tiny amplitude of the oscillation. And then you have an omega A, which is this oscillation frequency. And then a phi is the starting phase where you start, what point you start, yeah. So it's a 5-parameter fit function. You fit that, and you extract from your fit this omega A, and boom, you have an answer. But actually, life is not that simple. There are beasts. By beasts, I means it's an experiment, and it has limitations. It has, various errors entering. For example, when you are injecting your muons inside the ring, you don't inject it exactly in the orbit, stable orbit that you want. You slightly put an angle, if there is slight angle along, even a milliradian angle when you introduce the muons, into the ring, and you get an oscillation like this around the orbit. So this black bold line should be the ideal orbit, but what you get is this oscillation around this orbit, and that introduces another frequency in your in your function, and you have to correct for that, of course, and it's called a coherent Betatron oscillation correction. This animation, nice animation you are seeing, is actually a reconstruction of the muons where they decayed into positrons. So it's a map of the muon bunch, okay? Inside, I mean moving around the ring. So you see that they should be perfectly stable in the center, but they're not. They're like oscillating back and forth like this. All right, this is one of the beasts. Not so big actually, not so nasty. There are other nasty beasts. Okay, so there could be like when you insert the muon, you don't put it inside the exact hole. You hit the side and they interact with a wall and they decay there, and you don't get them in the orbit. So it's called a muon loss, and this is another error that will enter those nice plot, and they will give some errors, and you need to correct for those. Okay, then you have E field correction. So remember when we said like we apply electric field to focus them, but the cancellation is a magic cancellation. Well, I also said that there is a spread of the energy, so you don't get exactly one value for the gamma, but slight spread in gamma. So that's why you get a spread of that, and that's why the cancellation is not perfect, and you need to correct for that. We are looking for an amazingly precise experimental result, so you have to consider every possible error that can enter, and you need to correct for that. Okay. Then there is another thing called pitch correction, which is if the when you introduce it and there is an angle in the vertical direction, of course you apply an electric field from the vertical to focus that, but then it will be oscillating in the vertical direction slightly, and that introduces this another error that you need to correct for. Okay, then something called phase acceptance. So when you introduce a bunch, okay, a lot of muons you will be introducing. The muons that are in the center, they experience, so they stay in the stable orbit. The others oscillate more, and as a result of the spread, the middle ones have actually the mean energy value that you want, in the rest on the sides have different energy values. So they tend to, they're slower, right? So if the middle one have the energy of 3.1 GeV, let's say, the side one slightly less. So when they're revolving, the ones that are in the side will start to slow down, and so the bunch that you had will start to elongate, and so they decay in different position. And this will introduce another error which will make this initial phase that we'll say time dependent, and that also needs to be corrected. Okay, there are tons of other corrections, really. So many that there should be so many talks over that, and I can't do that right now. So I'm going to the next point. Well, remember that what was our formula for A mu? For that, we needed to calculate this frequency, this frequency omega, but then you divide by this quantity, and you need to know this magnetic field. And you need, of course, you are creating this magnetic field, but it doesn't mean that you know what you have created. So you need to measure this B quantity, the field strength, very, very precisely, amazingly precisely, and it has to stay also stable. So the animation here at the top is a trolley inside the ring that has a lot of probes that measure the magnetic fields. Every 3 days, we do this trolley run that measures this magnetic field. Is not there. And then there are some fixed probes. They are always there. So even when the muon is, and they're measuring this magnetic field all the time. So we know this magnetic field so precisely that even with a precision of 70 ppb, what that means is we know we can measure this so precisely that our error is 70 just in a billion. So imagine that, like in terms of percentage, okay, will be 7,000 divided by 1 billion. That's absolutely zero for this purpose. So that precisely we need to know the magnetic field if we want our final answer to be, precise enough for the g-2. Okay. When you put this A mu on one side, omega mu on the other side, and you divide by this B and the charge of muon and the mass of muon, it's a simple term, right? But in principle, it becomes a bit complicated because of the magnetic field. Because we really, don't measure the field. What we measure is, okay, let me go with their comments. How we physically include the concept of new force in this experiment. Yeah, I'm coming to that. In this experiment, we are not introducing any new force. In an experiment, you don't introduce anything. An experiment means that you don't know about anything. Let's say, of course, you know about how you calculate, but you are just measuring. Imagine like you were just measuring. You just holding a stopwatch and you're measuring the falling of the apple. I mean, whatever value you get. And if a theory doesn't explain that, that means that theory needs to be corrected. It's a theoretical problem. Experiment-wise, we are just measuring this thing, a physical thing, very precisely. Okay. So in principle, why this becomes a complicated formula? Don't worry about the complicated formula here. What it means is like the magnetic field that we measure using something called the nuclear magnetic resonance. So we don't measure really a field, but we measure how protons react to this magnetic field, how they precess in a magnetic field. And we measure the frequency of those protons. And that in turn gives us the magnetic field. So what we are measuring is the frequency of those protons. On the other hand, we are measuring the frequency of these oscillations that I said. Oscillations in the number of positrons that we detect. So in principle, in this experiment of g-2, what we really are measuring is the ratio of these two frequencies. And it has a lot of other terms, but they are like fundamental constants, like the magnetic moment of the electron, magnetic moment of the proton, mass of muon, mass of electron, g value of the electron that is known very precisely. Those things will come from externally, they are the fundamental constants, let's say, that we will use here to calculate. But what we are measuring in this experiment is basically these two quantities, okay? And for the precession frequency, or correspondingly the magnetic field, we don't need to measure the magnetic field everywhere. We just need to measure them where the muons will be. So how the muons are seeing that magnetic field, that much we just need. So we are measuring this part, and we need to measure this part with a precision of 140 part per billion. All right. The constants are very precisely known, 11 part per billion, this quantity. The next quantity is known as 0 part per billion, which means amazingly precisely that we don't even have to worry about. The next quantity is again 22 part per billion. Again, don't have to pay attention, it's amazingly precise. And this one is 0.3 part per trillion. Amazing, good news, okay. So this whole thing that is coming from other people, it's the calculation of other people, let's say, not Muon g-2, is less than 22 part per billion, their precision, which is we are extremely happy, it doesn't bother us. This part in red is what we measure. Okay, well, in the end, what we measure is the distribution of the beam, muon beam, and the magnetic field very precisely. We put this thing together, we got something like this, which actually represents how the muon distribution, or how the muons see the magnetic field inside the ring on the average over this whole ring, you know, and over the whole period of run 1, that the data that we are using. Okay, now here it's a very interesting concept for students actually, and also for physicists. It's called blinding, and it's very important. Okay, blinding in principle means, okay, this has to do with human nature actually. So pay attention. It doesn't matter how honest you are, you know. You could be, I mean, as Feynman said, like, it's easy to fool yourself, very easy. And you think you are extremely honest physicist. You are measuring something, you are analyzing, and you are calculating this quantity. But you have some ideas, right, about how the previous experiment found the value, or you have some ideas about what the theoretical number is, and your subconscious might trick you to push you towards a value. You might, I mean, not, you know, intentionally, but this can bias your analysis in ways that you can't imagine. And even if you don't want your results to be biased by your mind, but you could get biased. So what people do is they divide their analysis in various groups, and they don't discuss with each other until the last moment when they bring these information together from different parts. They get the final answer. Before that, they have no control, no idea about what these numbers is. But there is a trouble with this approach. I mean, there could be friends, you know, casually discussing, you know, my value is maybe this, what's yours? And they're probably drunk or something, and they reveal, and, you know, here goes the bias. So we can't trust ourselves. We can't trust our nature. So g-2 Fermilab came up with this particular way of blinding, which is amazingly clever. They said, okay, let's say we don't trust anyone, we don't trust ourselves. Let's give it to, I mean, let's keep it a secret for the whole collaboration. So we invited this 2-person scientist from the directorate of Fermilab, Greg and Joe. They are not from our collaboration, and they're from the directorate. So we don't want to show our dishonesty to them or reveal anything to them. And we can't ask them, or they can't talk to us about this. So, and they're not noting down what they did. So we invited them and asked them to, you know, go inside that room that has our master clock. Because, you know, we measure time in our experiment, time for everything, for analysis, for when the muons entering, when they're decaying. They're all measured in terms of a clock, right? And that clock has to be common to all of us, so that we don't introduce a relative delay between various clocks. So we have one GPS-based clock, inside the internal room. And everything is measured in terms of that clock. And you know, a clock always has a frequency, and digital clocks have frequencies that can be changed, that can be adjusted. So what Joe and Greg did is they changed that frequency of the clock randomly with a random number, but only slightly, you know. And they wrote down their number inside a cabinet, locked that cabinet inside two envelopes. But they too did that inside the envelope. They changed our frequency of the clock and put it inside a box and locked it and took the key away before, our run even started in 2018. Okay? Before our run 1 starts. So we don't know what the frequency is. So what we know is a relative number we call a factor that we don't know. So what we know is what the clock is showing, a number, but it's a false time. It's not introducing any error, because let's say it's like you were stretching the time. I really invite you to watch this video on YouTube. Why is the Muon J-2 experiment shifting time? Very interesting. Okay, so it's like stretching the time slightly and measuring everything in terms of that particular time, which means our results will be in terms of this particular clock time, and this result will not be a physical result. And so, as we don't know what this number means, there is no way of, should I increase this number? Should I decrease this number? Our subconscious wants to do something, but it's blind. It can't do anything right now. So that's what the aim was. It's a security. Okay, so this is blinded. Our experiment is blinded. So the final result is a complicated formula like that. In front of this whole formula, in the end, this factor f clock should be multiplied. That we don't know. So what we know is rest. We know the rest. Without this particular factor, there is no physical meaning to this. It's a result, but it's a relative result that you cannot tweak in this way or that way to match with anything. So yeah, even if you're biased, this is not getting biased. You don't know which way you should bias. Okay, so in the end, when I said like lots of corrections, this correction, that correction, pitch correction, coherent oscillation and all, in the end, this whole 5-parameter simple fit function that I said, one decay exponential and another cosine, becomes a messy, huge 26-parameter function. But we do it very well. We do fit it over this whole 11 billion positron events, and we get numbers out of it. These are various errors on those numbers. They're tiny. So in the end, we get a precision on our result of 462 part per billion. Okay, sorry, it's not million, it's part per billion here. Okay, that's our precise result. Is there a question? No. So that's our final result. I see that, okay, the numbers are staying almost stable, only 3 decayed in our participant particles. Okay, all right, so let us unblind. So on 25th of February, when we were absolutely sure about our analysis, our calculations. Oh, and remember, there were 6 analysis groups all around the world. They don't talk to each other. They do their own analysis in using entirely different methods, so that things are as independent as possible, so less and less biased, and they're blind again, and they're relatively blind to each other. So when we're absolutely sure, okay, whatever we find, it could be a nice result, bad result, we don't know, but we are absolutely sure about our result right now. We all agree to our relative terms, it's not a bad result, that was a bad term. We matched our results, these relative results, and they looked beautiful, consistent, but relative, different, but in a stable way. So we said, okay, our result is final, we final. Of course we came to this result years ago, but we had to correct for everything, so we spent a lot of time for that. So when I was a run coordinator, we were actually doing these a month, devoted to this kind of fixing things. All right, let us unblind. So all of us came to Zoom and we unblinded. Okay, so it was really an exciting moment, a really exciting moment for all of us. And of course, 7th April this month, so we took some time to write down the final forms of our papers. There were 4 papers coming up. You see the diversity of our collaboration, PRL paper, then PRD is the particle physics thing here. Then atomic and nuclear physics, accelerators and beams physics. There were even optical physicists. The Italian group was doing a lot of optical stuff that I'm not going into the details. So these diverse papers came out on that day where we announced our results. Chris and Graziano came live from the Fermi Lab channel when they announced these results. And it created a wave across the world. Because, our result was like 0.46 part per million, but our result, you see, within the error band, verified that the last results 20 years ago was correct. They did the experiment, we confirmed their result. So that means a high, amazing confidence that the previous result was right. So the result that came out was not wrong. There is something going on, the difference between the theories and experiment. So we combined our result and their result, and the final total experimental value of the anomalous magnetic moment of muon, which is g-2/2, we found this number with a 0.35 part per million, 350 part per billion, amazingly precise. And we saw that our value, the experimental value, differ from the latest theoretical result by 4.2 sigma. Previously you saw that 3.7 sigma, the difference now increased, So that difference is now bigger. So we have amazing confidence. The thing is, this result is based on only run 1 data collected during 2018 and 2019. We have 4 more years of data, 1, 2, 3, 4, and the final one, 5. After this whole 5 years, when even next year actually, we might get a value greater than 5 sigma. And if you get that, that means clear discovery of new physics, which means something new needed, like an unknown force or an unknown particle that we don't know is contributing to this magnetic moment of the muon that is not showing up in our theoretical calculations because we don't know those particles, so we are not considering the contributions from them. So, maybe the next year when we publish the run 2 results, we'll be already crossing that bar. But remember that the theoretical result will have to be more precise also, because you are comparing this versus this. If this is small and this is big, error bar, it's bad. So you need really a good precision in both cases. In our experimental measurement has to be precise, our theoretical measurement has to be precise. All the theoreticians must agree that yes, this is our final result, and so on. So here I put names of some of the new physics that might. I'm not going to discuss them, but I invite you, because this will take a whole new talk, to go to this particular link. You can take a screenshot now, or from the stream video later you can take it, and you can go to this particular talk and you see a very detailed discussion on what are the kinds of new physics that might explain this. Because, you know, as the tension grows between the theory and experiment, many people already started years ago to develop new theories, okay, new models, and they will create, and those new models, you know, when you calculate your magnetic moment of muon, the G factor, using those new models that some physicists came up with, new ideas, when you calculate using their, you know, these unknown particles, now they're called leptoquarks and so on, 2 Higgs doublet model, let's say, these are the names of models, supersymmetry, maybe you have heard about. Use those models, and I mean, you can also use those models to calculate, consider those particles in the vacuum popping up and contributing now to your loop of this particular calculation, and see what extra value you get, right? Okay, and then you add this extra value to your already existing standard model result, and now the total value, does it now explain the new experimental value? Okay, let's say, so what does it mean? Let's say some XYZ 3 models, right? Some guys gave this X theory, some gave this Y theory, some gave this Z theory, and according to, so in these 3 groups of people will calculate their own contribution of G minus 2 and will add to the known value, and they will get some values, right? Final values of the not be standard model, but will be these new physics answers, okay? And if one of those values come and fall in this bar here, that would mean that that new physics theory is correct, probably, you know. Of course, it will have to explain other things too, but at least as far as the G-2 test goes, this theory is good. I mean, it's also possible that out of 10 new theories, 3 of them will be able to explain this experimental result. The difference between their calculation and this value will not be significant. And the rest, you know, 7 will get an answer that will be outside. And in that case, we'll say, okay, those 7 new theories are bogus, discard them. And that's how we actually discard bad theories. Okay? So, yeah. Yeah.
Yeah. So we have only this meter is scheduled up to 7:30.
I think I'm done actually. So yeah. I'm done. It's like couple of minutes.
Okay,
maybe.
so just keep a couple of minutes.
Yeah.
Yeah.
Okay.
Yes.
Yeah. So that's what it means. So this is the last slide where I wanted to put this animation of inside the ring, that is what the muon sees inside the ring. This is a simulation. Here we have the traveling across the ring. On the right, we have how we are progressing on collecting data. So this was run 1, 6% of our target value in statistics. We completed run 1, 2, 3, most of the 4, and in October this year, we will be starting the final run. And by the end of that, we would have achieved the final goal of 20 times, 21 times actually, the data collected compared to the last experiment at Brookhaven. Thank you. Now, I'll, any questions if you have so far?
So, you can unmute. You can. Okay, thank you, Tunu. Thank you very much. So, all of you can unmute your microphone. So, I think already some questions are there. in the right panel in chat box.
Yes.
So we'll try to.
Yeah. Yeah.
Short answer is
Okay. Okay.
possible,
Yeah. Go
but
ahead.
it may mind in the time constraint.
Okay. So yeah. So whoever is going to ask a question, you can type, and I mean, someone wants to say something, they can unmute only one at a time. Yeah.
Already been asked.
Okay.
Just
Okay.
check this.
So I think I answered all the questions that were asked before. I see the last answer. Apart from G-2 experiment, are there any other experiments which could indicate new physics? Yes, there are many experiments actually. In fact, yeah. Yeah.
I will be only this meeting scheduled up to 7:30. Okay.
Okay, okay. Yeah, so we have 15 minutes, you are saying, or?
I think it is time left. Forget it.
There is no time left, that's what you're saying? Sorry? I see it's 7:15, so I don't know. I mean, can you please repeat what you said? It was breaking out, so your voice. Sir? Okay. Okay. So apart from G-2, Nibir asked this question. Okay. Yeah. In fact, all the particle physics experiments are looking for new physics. For example, apart from G-2, the strongest signal came from neutrino experiments. Because, you know, as far as I discussed previously, that neutrinos, according to standard model, has to be massless. They are like photons in that regard. They are massless. But one property of neutrino is called the neutrino oscillation, where one kind of neutrino converts into other kind of neutrino. And to explain that, it is required that the neutrinos to have mass. However tiny, but they should have mass. So there are ranges of experiment. I mean, over over the decades, we're doing neutrino physics experiment that are looking for new physics. Of course, this oscillation is a sign of new physics already, which means that we need new physics. G-2 is the next strongest in that way. One problem with the neutrino is that you don't have enough data. Neutrinos interact hardly, so you don't always have, it's extremely hard to reach the 5 sigma, which means you need a lot of data. So you have Dune experiment, you have Nova experiment right now, that is a big that I'm a member of, and it's also looking for new physics. Dune is going to start another neutrino experiment. Then there are dark matter experiments, Xenon experiment of Gran Sasso, Italy, that my previous group is involved from Naples. I mean, I can name plenty, but yeah, you can look for it. All these, they're looking for dark matter, which is another thing that is beyond standard model new physics, of course. Okay, another question about the cancellation of electric field component. We're choosing muon energy relating to A mu while measuring A mu. Very good question, Devender. This is a very good question. Yes, so how can we do that? I mean, we don't know A mu. We are measuring A mu, yet we are using a gamma value to cancel this A mu. How does that work? That sounds crazy, right? Well, we know A mu from our previous experiment, from our theory, but with, let's say, with an error bar. We know what the range is, of course. I mean, what that range is. So if we choose any value close to that number, the error that we introduce in this calculation is so tiny compared to the energy distribution of the muons. So effectively, it's compared to the uncertainty in the energy of the beam, which relates to the uncertainty, the gamma factor, it's nothing. Okay, so that if that answers the question. Any other questions? I don't see any other questions though. We have about 10 minutes.
Excuse me, sir. I'm Sahil Nath.
Okay, go ahead.
So what happened on 7th April? Because you said something like the assumptions before 7th April 2020.
Okay, it's not assumptions. So before 7th April, we did not declare our result. So only experimental result that was available was from the last experiment that was published 20 years ago. So before 7th April, theoreticians put up their theoretical calculation and they compared it with the result from 20 years ago. After 7th April, of course, the new experimental result is available. So they compared it with a new result and came up with more tension between theory and experiment.
Thank you, sir. Actually, I misunderstood us earlier.
Oh, okay. I hope this clears this up. Okay. Okay, more questions? You can type actually here.
So, I have one question.
Go ahead, sir.
Like, is there any signature of maximally or minimally supersymmetric model to take care of that extra extension of that moment?
I won't be able to. Yeah. Okay. I won't be able to give a precise answer right now for that because I don't know the exact calculation. But as far as I know, supersymmetry gives a very precise answer to the contribution to the mu in terms of the beta factor. It's like theta factor of weak interaction, you know. This is very sensitive, which means the their value. Okay, so which means actually a mu will be able to very precisely discard or accept the result from the supersymmetric models, various. A mu, I mean, there is already so much data from LHC, but they are like unable to differentiate between many models. They're degenerate, let's say. A mu is such a beautiful quantity that it actually differentiate between different theories very quickly because all these different theories produce very largely different values for the mu. Sorry for the not maybe giving you the exact number or anything on the supersymmetric, maximally supersymmetric models, but yeah, I mean I can if I'm still sharing, I have, if you are interested, because this is like a gold mine here. This particular talk that has extensively devoted slides on almost every new model. Okay. Any other?
Hello.
Yeah, your voice. Oh, Subhash, your voice is breaking a bit. Okay.
I have a couple of questions.
Go ahead.
So the first one is on neutrino. You mentioned about the new experiments going on.
Yeah.
As far as I know, the present successful theory about neutrino mass is the MSW model, right?
Yeah.
The Wolfenstein mechanism.
Mm-hmm.
So and that actually is within the boundary of standard model.
Yes, so you can say like standard extension, right? It's not. I mean, standard model absolutely. The pure standard model absolutely do not have neutrino mass. So that will be the next extension, keeping everything else the same. Yeah. Okay. Yeah. Go ahead. If you have. I mean, if you want to.
Yeah. So in that model, if I remember correctly, it's weak interaction.
Mm-hmm.
So if it is only weak interaction, then maybe it's within the boundaries of standard model.
Okay.
Otherwise, maybe we might have to, and there are some new aspects also. And there is a second question.
Mm-hmm.
I have already discussed this question with you previously, actually.
Okay.
What about the new results of the lattice theory? I mean, the BMW.
Okay.
Results.
All right. This is a question that everyone asks, and Fortunately, they don't put us in much trouble or shame, but they create a problem in the theoretical group. So I discussed that there are, for everyone, that there are two approaches. One is the dispersive approach. The other one is Lattice Qcd approach, discrete spacetime. So these theoretical initiative paper and the result that came out, they were consisting of these two approach. All the lattice people and all the normal dispersive people came together and put this result. But there is one group called the BMW. They published their result recently, separately, alone. And their result differs from the rest of the theoretical people. They're lonely in that case. And they are saying that our result matches with the new experiment. So there is no new physics required. And there.
Okay, so we are going to finish.
Yeah, we have.
Because we schedule
Okay.
to finish by 7.